All right, today we're going to break down a really core concept in operating systems. It's called preemptive priority scheduling. Now, that sounds complicated, but it's really just how your computer decides what to do right now. And trust me, it's way more intuitive than you think.
So, to get our heads around this, let's start with a really simple question. Imagine you're an ER doctor. You've got a patient with a broken arm, and then suddenly another patient is rushed in critical condition. What do? Well, you drop everything and switch to the critical patient, right? Of course you would. And believe it or not, that exact same logic is what computers use every single second to manage what they're working on. So let's dive in.
That whole ER scenario, it brings us right to the core idea here. Priority scheduling. I mean, at its heart, it's just this simple recognition that, well, not all tasks are created equal. Some things are just more important than others.
So here's the formal definition. Every single process or program that wants to run gets a priority number assigned to it. And the one with the highest priority, that's the one that gets to run first. It's kind of like the scheduler is a bouncer at a super exclusive club. It looks at all the processes waiting in line, checks their priority ticket, and the one with the highest number gets to go straight to the front, right into the CPU.
Okay, but what happens when a new, super important task shows up while the computer is already busy with something else? That's where this key idea of preemption comes in. Think of it as the system's power, its authority really, to hit pause on whatever it's doing and immediately switch over to the more urgent job. It's the dropping everything for the critical patient part of our analogy.
And this difference between preemptive and non-preemptive is absolutely crucial. See, in a non-preemptive world, our ER doctor would have to finish setting that broken arm, no matter what, before even looking at the critical patient, which is, well, not great. But with preemptive scheduling, our doctor, the CPU, can switch immediately. This is what makes the system feel responsive and snappy. All right, theory is one thing, but to really get this, we've got to see it in action. So let's do that. Let's put on our scheduler hat and walk through an example step by step with 4 different processes and see exactly how this whole thing plays out.
Okay, before we start, we need one simple ground rule. For our example, the bigger the priority number, the more important the process is. So priority 40 is way more important than priority 10. Just keep in mind, in the real world, this can sometimes be flipped, so it's always the first thing you have to clarify. So here are our contestants for the CPU's attention. We've got 4 processes, P1 through P4. You can see their arrival time, that's when they show up, their burst time, that's just how long they need to run, and of course, the most important part for us, their priority. Okay, let's start the clock. Time equals 0. Right now, it's an easy call. The only process that's even here is P1. So with literally no other choice, the CPU grabs P1 and starts working on it. Okay, 1 second has passed. It's now time equals 1, and boom, P2 arrives. The scheduler looks at P2 and sees its priority is 20. Now remember, P1, which is currently running, only has a priority of 10. So what happens? Preemption. The scheduler stops P1 dead in its tracks, puts it on pause, and immediately switches the CPU over to the more important job, P2. And here we go again. At time equals 2, P3 shows up. Its priority is 30. The currently running process, P2, only has a priority of 20. So same story, different process. The scheduler preempts P2, puts it on pause, and gives the CPU to the new top dog, P3. All right, so P3 needs 2 seconds of burst time. It starts at time 2, so it runs all the way to time 4. And it's done. But at that exact same moment, at time 4, P4 arrives. And check out its priority. It's 40. That's the highest one yet. So, you guessed it, the scheduler immediately hands the CPU over to P4. P4 was a really quick one. It only needed 1 second, so it finishes at time 5. Now, things get interesting. For the first time, there are no new processes arriving. So the scheduler looks at its list of waiting half-finished jobs. Who's left? We've got P1 with a priority of 10 and P2 with a priority of 20. The decision is easy. P2 is more important, so it gets to resume its work. Now let's not forget, P2 needed 4 seconds total, but it only got to run for 1 second, way back at the beginning. So it still needs 3 more seconds. It runs from time 5 all the way to time 8, and now it's finished. And finally, who's left? Just one process, our poor patient P1. It finally gets the CPU all to itself to finish up. And here it is, the final Gantt chart. This thing tells the whole story, doesn't it? You can literally see the journey.
P1 gets 1 second, bam, interrupted by P2. P2 gets 1 second, bam, interrupted by P3. P3 runs to completion, then P4 jumps in. Then we go back to finish P2, and only then, after all of that chaos, do we finally get back to finishing P1. It's a perfect picture of what preemption actually looks like.
Okay, so this whole system seems great, right? It's super responsive. It always deals with the most urgent thing first. But there's a catch. Like with any system, there's a trade-off. And this one has a really big, potentially critical flaw that designers have to worry about. And that problem is called starvation. It's exactly what it sounds like. Just think back to our process P1. It had the lowest priority. Now, what if a never-ending stream of processes with priorities of, say, 11, 12, 20, 50 just kept showing up? P1 could get stuck in that waiting queue forever. It would literally be starved of CPU time and never get to finish.
So how do you fix this? How do real operating systems stop this from happening? Well, they use a really clever trick called aging. It's pretty cool. The longer a process has to wait in the queue, the higher its priority becomes. It's like it gets more and more important over time. So eventually, even our poor, low-priority P1 would wait long enough to age its way to the front of the line. It's a guarantee that everything will eventually get to run.
Okay, that was a pretty deep dive. So let's just pull back for a second and recap the absolute key takeaways from all of this. So, if you remember anything, remember this. 1. It's all about running the highest priority task, period. 2. Its secret weapon is preemption, the power to interrupt a running process for a more important one. 3. The big win here is responsiveness. The system feels fast because it handles urgent stuff immediately. 4. The big danger is starvation, where low-priority tasks could wait forever. And 5. The elegant solution to starvation is aging, where processes get more important the longer they wait. So there you have it, preemptive priority scheduling. It's a really powerful tool that's fundamental to making our computers feel so fast and responsive. But it does leave us with a pretty big question to think about, doesn't it? This algorithm is completely obsessed with urgency. But what about other things like fairness or making sure everyone gets a turn? A real-world OS has to balance all of that. And figuring out how to do it? Well, that's the giant, fascinating puzzle of operating system design.